Thank you very much, Daniele, for the kind introduction. My topic today is investigating the influence of hydrogen underground storage. For that, I integrated hydrogen underground storage into Pipes of Earth, and as it's yeah, right now a little bit early after lunch, I thought it might be a good idea to already start with the summary. If some participants get sleepy after some time, that they already have the most important stuff already beforehand. So um, within this case study, I integrated a geoinformation system-based hydrogen underground storage into Pipes of Earth. I applied it to Tunisia and then investigated the influence of hydrogen underground storage on the energy system design. Some highlights, taking into account underground hydrogen storage has an influence on the energy system design. It leads to cheaper hydrogen production costs and extending renewable energy in this case study is the most cost-effective solution. So let's begin with the motivation. There is a South H2 corridor planned from Tunisia over Italy to Austria and Germany. And Tunisia plans to export 200 terawatt hours of hydrogen in 2050. And to export that huge amount of hydrogen, there is a big need of storages to stabilize the hydrogen supply. Not only hydrogen storages, also battery storages to stabilize the energy supply for the electrolysis, but in general, a big need of storages to stabilize the hydrogen supply. And when we are talking especially about hydrogen storages, there is hydrogen underground storage in salt currents right now the most economic option for storing hydrogen. So one task for this case study due to this motivation would be to showcase the influence of hydrogen underground storage on hydrogen exports. But there's more motivation for me. There are only 54 scientific articles about 100% renewable energy scenarios for the whole continent of Africa. And what's really sad about that is also that 7 of them are about La Réunion, which is politically considered part of France, and not a single one is about Tunisia. And because of that, I want to verify also for Tunisia that 100% renewable energy extension scenario is the most cost-effective scenario, which would be task number 2 for this case study. Last but not least, the third motivation is that most of these 54 studies for the whole continent of Africa due to paper from Oyevo and Christian Breyer are focused on power system only. Many sectors are not integrated in these kind of studies, and one which is also most of the time not integrated is H2. And as Pipes of Earth lacks the hydrogen underground integration, at least the geoinformation system-based hydrogen underground integration, I thought a cool third little task for this case study would be to integrate geoinformation system-based hydrogen underground storage to Pipes of Earth. So as a little bit of a summarization of the task for this case study, I want to verify that a 100% renewable energy extension scenario is the most cost-effective scenario. I want to add geoinformation system-based hydrogen underground storage to Pipes of Earth, and I want to showcase the influence of underground hydrogen storage on hydrogen exports. So let's start with the methodology. It was kind of a little bit hard to implement it because I haven't found any global data sets which have capacities included within the data set. So the only thing I have right now is a global geoinformation system data set of salt currents, which provides the global distribution of the salt deposits. And as I don't have the capacities within that data set, I have to calculate it. And to calculate this, I need basically 4 steps. In the first step, I try to classify the deposits into domes, bedded salts, and also excluded deposits which are not suitable for hydrogen underground storage. So within this step, I'm trying to ensure that only suitable geological formations for cavern constructions are considered. In the second step, I will do some land use exclusions. So I try to apply a buffer zone depending on the salt type, which are basically depending on the assumptions on the right-hand side. And that is due to that there are different safety distances for domes and bedded salts, which we have classified in the first step. And afterwards, I apply the Copernicus land cover mask to remove unsuitable areas. And in the last step of this step, I apply a minimum structure size. Also, both of it is on the right-hand side are my assumptions for that, which land use exclusions I have used, and so on and so on. And in the end of this step, I then have only the technically usable salt structures remaining. So in the third step, I am now calculating the potentials. So I assume every cavern is moduled as a capsule based on the assumptions on the right-hand side again. This gives me then the cavern volume in cubic meters, and then I can basically, based on that cavern volume and the surface area of one cavern and the energy density, calculate the potential in megawatt hours for the specified areas. Then, last but not least, I have to get the potentials into our pipes to earth model. So basically, then I basically intersect the feasible areas for hydrogen underground storage with the bus regions of our model, aggregate it, and allocate it proportionally to the bus regions. So then in the end, we have our final data set, which is the geographically explicit storage potential, which is directly usable. On the right-hand side, you can see the suitable bus regions for Tunisia. And now I want to quickly show you the results for the case study for Tunisia, but it's in the end usable for every country around the world. Basically, one task of the case study was to integrate geoinformation system-based hydrogen underground storage into pipes to earth. We can check that. We successfully integrated it. It gets used, not really much, but it gets used at least. As you can see, the model, the model uses underground hydrogen storage in the 3 bus regions which are suitable. Then our second task was to verify that a 100% renewable energy extension scenario is the most cost-effective scenario. Now we have the current energy system of Tunisia on the left-hand side on the map, on the right-hand side in the pie chart, and the optimized version of the energy system for 2050 shows us that there will be a lot of solar and onshore extended. And also, if we are looking into the generator capacity expansion, we see that schist, solar, and onshore wind will get expanded, which means that the 100% renewable energy extension scenario is the most cost-effective scenario. So the third task was to showcase the influence of underground hydrogen storage on hydrogen exports. And I have to say, the influence on hydrogen exports, at least for Tunisia, is not that big, because basically our export buses are on the other side of the country, and very far away from the buses which are suitable for hydrogen underground storage. It gets used a little bit, but not that much as I thought initially. So basically, we cannot really check that. My assumption would have been that basically hydrogen underground storage will sort of be used instead of the H2 store tanks. But for the two scenarios with the underground hydrogen storage and the other scenario without the underground hydrogen storage, we can see that even more H2 store tank will be extended in the underground hydrogen scenario compared to the without underground hydrogen scenario. And the rest of it, there's slightly a little bit more H2 electrolysis used and slightly a little bit less steam methane reforming in the underground hydrogen scenario. And also when we are looking into the heating supply and stuff like that, we see that there's slightly a little bit more gas boiler used than heat pumps in the underground hydrogen scenario. But apart from that, nothing really changes. Because of that, I sort of adapted the task to showcase the influence of underground hydrogen storage on the energy system design. And if I not configure export volume from close to 200 terawatt hours of hydrogen exports, if I don't configure that and just optimize the energy system of Tunisia without any hydrogen exports, we can see a little bit of an influence of the underground hydrogen storage on the design. More pipeline capacity is extended at the regions where we have the underground hydrogen storage. Less is extended where we don't have the underground hydrogen storage. What we also can see is in this case, for these two scenarios, that as I thought initially, that more the addition of the underground hydrogen storage leads to less H2 store tanks. And what we also can conclude in this case is that in general, more renewable energy will be added in an underground hydrogen storage scenario. And because of that, the system gets more decarbonized. Exactly. We can see the effect also in heating and all the other sectors, transport and so on, that it gets a little bit shifted to hydrogen. And thank you for your attention. I'm happy to answer any questions, and I'm also very much interested in integrating other functionalities into Pipes-to-Earth. So right now I'm also trying to integrate desalination. Also, I want to integrate hydro potentials, geothermal potentials, and biomass potentials in the future, and also off-grid. So if you want to work on that, or if it would be a great feature for you and you want to use it as well, feel free to contact me. And also feel free to contact me if you have any sort of data sets for all of the integrations or stuff like that, or any hints. It's very much welcome for me. Thank you very much.
And thank you, Anton, for your presentation. Thank you once again. So now I think we can go with some questions. We have already 3 questions for you, but feel free to use the link that Theo pasted in the chat to keep asking questions. So the first one is, did you consider battery energy storage? Will hydrogen storage be more competitive compared to BESS?
Yes, I considered batteries energy storages as well. Hydrogen storage will be not more competitive compared to battery energy storages for most of the for most of the cases, but in some cases, yeah, we have at least some use cases for hydrogen storages as well.
Thank you. Second question is, what are your cost assumptions for other energy storage options? At what cost does hydrogen become more cost efficient than batteries?
Basically, all my cost assumptions are from the latest technology data repository. Yeah, so I don't know them out of my mind right now, but you can easily look them up. Yeah, and hydrogen gets not more cost efficient than batteries, just for some cases.
Thank you. And third question, what has been the effect of producing, storing, and exporting hydrogen in terms of the cost of electricity and flexibility of the grid in Tunisia?
So that's right now things I'm really trying to dig into, because all the stuff you have seen before are, yeah, just preliminary results. I trying to validate them right now and trying to analyze a little bit deeper. So I cannot answer this question to a like really good yeah, good quality, I would say. I guess I can answer it in some weeks, but I haven't analyzed that into detail yet.
Thank you, Anton. And also maybe a reminder, can be also useful for the other presenters. If you want to share any supplementary material even after the meeting, you're definitely welcome to do that. Maybe to provide it to us, and we'll be sharing it with the registered participants. Also, just a side note about your answer before about data for battery storage in technology data that's used in pipes and models. They come from the Danish Energy Agency assumptions from 2019. And then the last question here is, how was the optimization done? Was it least cost approach, or are you looking at the lowest marginal price possible?
Least cost approach.
Yes, and another question came up. We have time for that still. So, what is the year considered for this future hydrogen scenario?
2050, and a hydrogen export from, I guess, 199.8 terawatt hours, which is also in the hydrogen strategy of Tunisia.
Great. Thank you, Anton. Thank you again for your presentation and for your answers.